Sometimes taking a single experimental measurement just isn't enough. Sometimes taking an experimental measurement at room temperature only doesn't cut it. To understand the mechanisms that govern how our materials behave, we often need more than our conventional equipment can provide. For example, consider a standard tensile test of a metal alloy.
The micromechanisms active during deformation determine properties like the yield stress and elongation to failure. And to work out what these mechanisms are, we can usually only examine the sample in the microscope after the test, not during.
But there is another option. We can tension a sample inside an electron microscope, in situ, and through the use of digital image correlation, we can observe the micromechanics evolving step by step in incredible detail, providing bounds of information about the material. Sure, there are issues with shoving a tensile testing rig inside an electron microscope, and there are some hurdles with the data acquisition, but the scientific benefits far, far outweigh the downsides.
What about samples we want to examine at elevated temperatures, say for studies of grain growth or phase transformations? Well, we insert a furnace inside the microscope instead of a tensioning rig. This usually consists of an element inside a stage add-on that heats a small sample.
Again, there are some hurdles, the most important of which is making sure you don't melt the microscope pole piece or the detectors, but we've got pretty good at sorting these problems within the community. One significant limitation has been the user interaction, the fact that we have to constantly manage these experiments by hand at every stage. Let me give you an example from my own experience.
With the much needed help from my colleague Dr. Jack Donoghue, I started investigating phase transformations in titanium alloys with an in-situ scanning electron microscope heating stage in 2018. We used an FEI Nova scanning electron microscope equipped with a Gatan in-situ heating stage and an Oxford Instruments Nordler's Max EBSD detector. The goal was threefold. 1. Watch the recrystallization behaviour during the phase transformation during heating to 1000 degrees Celsius. 2. Watch the grain growth in as close to real time as possible while holding at 1000 degrees C for as long as possible. And 3. Watch the phase transformation in reverse in actual real time to understand better the effect of cooling rates. We couldn't have done any of these things without the in-situ heating stage.
This is how the experiments ran. We set up the heating stage in the afternoon on the day before the experiment needed to be run and loaded the sample, leaving the microscope chamber to pump overnight to reach the best vacuum as possible to avoid residual gas effects. We'd return at 9 AM the next morning to run the experiment, and we'd need to be done by 3 PM to take the heating stage out of the microscope by 5 PM. Fortunately, we could complete these sorts of experiments within the time frame. The experiment itself required Jack and me to be there most of the time, constantly fiddling with the microscope and the heating stage control. Fun experiments, but hard work.
Our initial experiments consisted of a series of short electron backscatter diffraction scans, or EBSD scans, to track crystal orientations over time and temperature, or we were using secondary electron imaging to video the sample surface changes in real time, like you can see here. Due to thermal expansion and contraction of the sample, this required us to constantly relocate our region of interest, which we tracked crudely with a sheet of marked acetate stuck over the microscope computer screen. We had to repeatedly adjust the focus, and we had to manually start all videos and EBSD scans, all the while keeping an eye on the heating stage control. It was a two-man job, a stressful two-man job.
We collected some excellent results with this setup, but our main limitation was the total experiment time. Jack and I are dedicated scientists, but we certainly weren't going to spend days without sleep to conduct a longer experiment. I dreamed of the day where we could run experiments that lasted days or even weeks. It turns out, I didn't actually have to wait that long.
Early in the year 2020, our TANIST laboratory was opened at the University of Manchester. This dedicated in-situ testing facility was designed and brought to life by Jack and pulled equipment and expertise from electron microscope creators Tescan and testing rig designers NewTek. This is where the name TANIST comes from, Tescan and NewTek in-situ testing. The lab now consists of 2 Tescan scanning electron microscopes, equipped with new tech heating stages and multiple mechanical testing rigs that fit beautifully inside the chambers. It's also fitted with state-of-the-art detectors from Oxford Instruments.
And the best part? It's all fully automated. You literally load your sample, align the electron beam, define your areas, set your experimental parameters, and then you hit go. Then you can sit back and relax, or, well, leave and go do something else. The system is equipped with autofocus, so no more manual adjustments for this. It uses little markers to track your regions, and you can do many, many regions. 24 is the current record. The software will control your heating stage or your mechanical testing rig, and it knows exactly when you want to take an image, run an EBSD scan, or start a menagerie of other possible data acquisitions. The specific experiment I want to talk about in this video is important to me because it's an experiment I always wanted to do with the old fully manual system, but I never could. Watching metal precipitation evolve in real time.
I'm a big fan of magnesium alloys, which I know is a fairly niche area of research. One of the most commercially used magnesium alloy systems is the magnesium aluminium zinc system. With a high aluminium content, these alloys exhibit age hardening from precipitates, like many aluminium alloys do, and love to reap the benefits of this strengthening. However, there's an issue. We want the alloy to form lots of tiny strengthening precipitates within the microstructure, but it has a tendency to form a combination of these with large, useless particles instead. The strengthening precipitates you can see here, they form throughout the microstructure near homogeneously, so we call them collectively continuous precipitation. The unwanted stuff we call discontinuous precipitation because, as you can see here, it forms in only certain places, growing out from grain boundaries. The particles don't really contribute to strengthening at all. Theories suggest discontinuous precipitation uses up solute that the continuous precipitation needs, preventing more forming, lowering the alloy strength. So, the maximum strength obtainable through this mechanism is dependent on suppressing the discontinuous precipitation, and to do that, we need to understand how it forms. It is believed that both precipitate types form and grow at the same time, but eventually the discontinuous precipitation sucks the aluminium solute out of the magnesium matrix, stalling the continuous precipitation formation. But here's the issue with studying this precipitation. These processes require elevated temperatures to activate, and since we think they're in competition with each other, we need to see them evolve in real time. What I'm saying is that we need an in-situ heating experiment in an electron microscope with enough resolution to resolve the precipitates.
So why couldn't we have done that with the old setup? Because the full heating cycle takes days. No way we could have achieved that with a manual in-situ experiment without sacrificing a lot of sleep. The TANIST microscopes, however, are perfect for the job. Here's what we did.
Relying heavily on the vast experience of our TANIST technical specialist, Dr. Albert Smith, we put the sample in the microscope on the in-situ heating stage, chose our area, took an EBSD map of the grain orientations, we placed a hardness indent in the sample centre as a tracking marker, we determined our experimental beam conditions, and then told the software to heat to 180 degrees C. Which, interestingly, was the maximum we could get to, really, as the zinc sublimates at 190 degrees C under vacuum and would coat the electron column. Not ideal. After the temperature was set, we programmed the software to take backscatter electron images continually for as long as we wanted. Once running, we packed up our things and left the kit to run overnight.
Initially, we left it to run for 20 hours, continually collecting images for us. Once the sample was allowed to cool down and freeze the aging process, we took another EBSD scan, then repeated the heating and imaging cycle for another 20 hours. I then compiled the images into videos, and this is what we collected.
We took around 800 micrographs during the experiment. The imaged area overall was 200 by 200 microns at 4K resolution, capturing many grains because we couldn't guarantee where the discontinuous precipitation would form. I've zoomed in on 2 areas out of the full high-resolution video we captured. First, you can just about see the continuous precipitation form within the grains. These are the tiny white dots. Then, the discontinuous precipitation appears at the grain boundaries and storms across the grain, eating up the continuous precipitation as it goes. Clearly our theory was wrong. They are not in competition. It just seems that way when you look at this sort of microstructure after the heating cycle at room temperature. You can see that as the discontinuous precipitation front invades the grain, it coarsens and joins up the continuous precipitates to create large, useless particles that we so hate. In this section, you can see more clearly the stop-start motion of the discontinuous precipitation front, like it's getting pinned at various points in the microstructure. What is also clearer in this region is the grain growth that accompanies the discontinuous front. The backscatter electron imaging clearly picks out the crystal orientation difference between the grains with contrast, demonstrating the grain boundary is actually moving with the discontinuous front.
Over our 40 hours worth of data collection, consisting of correlative backscatter electron images and EBSD maps, this is some of what we discovered. The continuous precipitation forms first and is incorporated into the discontinuous precipitation as its growth front advances. Second, the discontinuous growth front is pinned by the continuous precipitates for hours at a time, especially when the continuous particle is orientated with its larger dimension perpendicular to the growth front. Third, while pinned, the discontinuous precipitation front needs to gather aluminium solute first to fuel its continued growth. And four, for the discontinuous precipitation to form, neighbouring grains required a misorientation of 10 degrees or more. This is a wealth of knowledge we would never have been able to obtain without the automated in-situ testing capabilities of our TANIST lab. And what's more exciting is that the capabilities are improving all of the time, pushing the limits of data collection areas, temporal resolution, and mechanical and heating capability. I've included links to the TANIST lab and related papers below.